In this video, we're going to be looking at proof. Now, it'll be a good idea if you look at the videos on sequences first before you do this video. Now, proof is a difficult but a very fun topic when you get used to it. So, let's make a start then. So here we've got 5 expressions, and for each expression, I've written out the first 5 terms. And what I'd like you to do is pause the video and write down what you can say about each sequence. Think of something to describe each sequence. For example, is it odd? Is it even? Are they prime numbers? Something along those lines for each one. Okay, so let's see how many of them you got right. So let's look at the first one, 2n plus 3. Now the only thing we can notice about numbers in this sequence is they're always odd. How about the second one? So they're not odd or even because they've got both odd and even in them. But we do know that every number is a multiple of 5. So that's what we can say about the second one. Every term is a multiple of 5. And the next one, we notice that every number is even. The sequence 4n plus 6 has only even numbers. Now the next one is a little bit tricky. n squared plus 2n plus 1. And if you said all the numbers are square numbers, then you're right. All the numbers in this sequence are all square numbers. It's a difficult one to spot. And the most trickiest one I have is the last one. n cubed plus 3n squared plus 2n. What can we say about this sequence? Now there's a couple of things you could have said. One of them being all the numbers are even. But the one I was looking for is that every number in this sequence is a multiple of 6. So how does proof work? Well, here we just looked at the sequence and said what we think they are. However, the sequence could suddenly change. If we looked at the 6th, 7th, 8th term, suddenly the sequence which we thought was all even might suddenly have an odd. Of course, some of them we can confidently say that won't happen, but with proof, you have to prove it. You have to prove it's true for all terms. And we do that algebraically. Okay, so how do we do this algebraically? So first, we let any given number be n. So n represents all the integer numbers, 1, 2, 3, 4, 5, and so on. So when we're talking about a number, we just say n. n is a general number. So how about 2n? What is 2n then? Well, try putting in some numbers. Put n in as 1, 2, 3, 4, and see what sort of numbers you're getting. If you put n in as 1, we get 2 times 1, which is 2. If you put n in as 2, you get 2 times 2, which is 4. Put in a few more and see what you notice about the numbers. So I've got the first 5 terms here, and we realize all these numbers are even numbers. And that's what 2n is. 2n is generally all the even numbers. So when we're generally talking about even numbers, we say 2n. So algebraically, all even numbers can be called 2n. So this is one of those you have to memorize, that 2n is a general format for even numbers. When you're trying to prove an expression is even, it doesn't have to be 2n. It can be in that format, 2 times something, because that's what 2n is, 2 times n. So it can be 2 times, and you can have a whole expression in the brackets. If you've done that, and you've put it in that format, you have proven that it's even. So whenever you want to prove that something's even, just try to factorize out 2. So here we've got 2n plus 1. Again, try to put some values in as n. Maybe put n in as 1, 2, 3, 4, and 5 and see what you notice about this sequence. And these are the numbers we've got. 3, 5, 7, 9, and 11. And what you should have noticed is that they're all odd. And this is another one you have to memorize. 2n plus 1 is a general format for odd numbers. So if you've got an expression and you're trying to prove that it's an odd expression, you want it in that format 2n plus 1. So what you want to do is try to factorize out 2 from that expression and leave 1 outside. We're going to show examples of this later, so if you're not sure what we're talking about, don't worry. Just carry on watching this video and memorize these ones I've asked you to memorize. So far we've memorized that 2n is for all even numbers, and now 2n plus 1 is for odd numbers. Okay, now we've got 3n. So again, put some numbers in as n and see what you notice about this sequence. So here we've got the first 5 terms, and you should have noticed that they're all multiples of 3. So if you want to prove that an expression is multiple of 3, just simply factorize out 3 like I showed you here. If you manage to factorize out 3 without any other numbers outside, so you don't want 1, 2 or any other number outside, then you've proven that this expression is a multiple of 3. And we can do the same for this one. Let's put some numbers in. So I've put n in as 1, 2, 3, 4 and 5 to get the first 5 terms. And we notice that they're all multiples of 4. So very similar to multiples of 3, you want to just simply factorize out 4. And if it was multiples of 5, you'd want to factorize out 5. Multiples of 6, you want to factorize out 6, and so on. Okay, so here's one of the expressions we had in the start of the video. And we said that this expression gives multiples of 5. But now we want to prove it. Because remember, it could suddenly change. Although we're confident it won't, we need to prove that. Okay, so what we're going to do. Well, remember what we did with multiples of 3. We simply factorized out 3. And for 4, we've simply factorized out 4. So to prove that it's a multiple of 5, you're going to try to factorize out 5. And if you can successfully do that, you've proven that this expression is always going to give you multiples of 5. And brilliant, that was so easy. We just factorize out 5 and we prove that this expression will always give out multiples of 5. Okay, so here we've got another expression, 4n plus 2. And we need to prove that this expression is even for all integer values of n. So think back to even expressions. What was the format? And you should have said 2n. You want to be able to factorize out 2 from this to prove that it's an even expression. So let's just go ahead and do that. And wonderful, we've simply factorized out 2. And I'm assuming that you're good at factorizing because this is a higher level topic. And since we factorized out 2, we've got it in that form 2 times something, 2n. So this expression is definitely even for all values of n. Here's another expression from the first part of the video. And we said this expression always gives odd numbers. Now we want to prove it that it always gives odd numbers rather than just looking at it. Remember that all odd numbers are in this format, 2n plus 1. So you want to be able to factorize out 2, like here, and leave 1 outside. If we can do that, we've proven that it's odd for all values of n. So let's try that. So remember, we're trying to leave 1 outside. So I've split that 3 up into 2 plus 1, because that's still 3, remember. And I'm going to factorize that 2 from the rest of it, leaving that 1 outside. Brilliant, it's in that format. 2 times something, of course that something is n plus 1, and a plus 1 outside. So we've proven that this expression is odd. Yes, we knew that it was odd from the numbers it was giving out, but this is how we prove it. It's in this format. 2 times something plus 1. Okay, so here's a tricky one. And if you manage to say that this expression is giving all square numbers, you've done well already. Now we're going to try to prove that. Let's start by trying to factorize this. And I'm hoping you're good at factorizing quadratics. So it's n plus 1 and n plus 1. Well, that's great, because you can simply write that as n plus 1 squared. So you got it in the format of a square number. And we've managed to prove that this expression will always give out square numbers. So although it seemed tricky to prove that this always gives square numbers, it wasn't too bad. And when you haven't got an idea what to do, just do what you can. And here, factorizing just seemed the way to go. Okay, so here we've got a tough question. And all the rules we showed so far won't quite help you in this one. We've got n squared plus n. And we need to prove that this expression is even for all values of n. Now, how on earth are we going to do that? Because for even numbers, we need to try to factorize out 2. So we're very stuck. And you might even say that, oh, this is not an even expression. However, go ahead and put some values in as n. And you'll notice quickly that it only gives you even numbers. So it is most likely an even expression. But how do we prove it? Well, let's start by doing what we can. It's very tempting to look at this and want to factorize it because both terms have an n in it. So let's start by doing that. Okay, so we managed to factorize it. Now what? Well, we're trying to prove that it's even, and it doesn't look like there's much more we can do. We're going to have to do some explaining to prove that this expression is even. Now remember, n is a number, any given number. So if n is a given number, what is n plus 1 then? Well, n plus 1 will just simply be the number after that number. So here we've got a number multiplying a number which is directly after it. So basically we've got two consecutive numbers multiplying each other. For example, 5 times 6 or 50 times 51. But we've got it in the general format. A number, n, multiplying a number straight after it. Two consecutive numbers. Now take a moment, pause this video and have a think. Can you say something about this situation? Okay, so what you could have said is if you have two consecutive numbers, one number after the other number, one of them is definitely even. Because you can't possibly have two odd numbers in a row. And an even times an odd, or odd times even, because we don't know which way around it is, either way, is always even. Or you could say, well, one of these numbers is even, therefore you should be able to factorize out 2 from the whole expression. So for this one, we actually needed an explanation to prove that it was even. It wasn't as easy as the other ones. We just simply factorize out 2. And there we have it. I hope you found that video useful. Support us by liking, subscribing, and share this with your friends. And if you still got some more questions on anything, drop a post on our forum at examqa.com where you'll find your questions answered.